In this lecture, we're going to essentially cover why vaccination is the most efficient control method for infectious disease and why we always discuss it like that. And that comes down to this key and central concept of herd immunity. So we're going to spend a lot of time talking about that, introduce some extensions to the idea of the basic reproduction number, the idea of effective reproduction numbers, and the concept of the critical vaccination threshold for an infectious disease. We're also going to look at these sort of theoretical results in a broader, more applied perspective by thinking about how we actually can use vaccines to eliminate endemic diseases. And we'll frame that around looking at smallpox, the only human infectious disease that we have so far managed to eliminate. Those benefits that we get from vaccination can also have unintended consequences or perverse consequences. So we're also going to talk about that in the context of rubella, which is a particularly important example of that. And then finally, we're going to think and delve again into this idea of how we deal with more structured populations than those that are just well mixed and what implications that has for vaccination strategies. Okay, so we saw yesterday that we can, by thinking about the criteria for when an epidemic ends, we can essentially manipulate the initial conditions of our model, at least, to prevent a single epidemic from happening. So provided, so an epidemic can only spread when the proportion of susceptibles in the population is less than this critical value of 1 over R0. So if we manage to manipulate our population such that the proportion of susceptible individuals was always exactly equal to or less than 1 over R0, then, at least in our deterministic model world, we would never see the epidemic spread of an infectious disease within that population. Okay? So, simple example here, we've set an R0 of 1.5, a recovery rate of 1, so an average infectious period of 1, population size of 100, start with a single infectious individual, but only 30 susceptible individuals. Okay? So in this case, instead of seeing an outbreak, the number of infectives immediately drop down from 1 and then asymptote towards 0. And there's a small change in the number of susceptibles and recovered individuals. Okay? So nothing happens. Brilliant, that's what we want. This population, we would say, has been protected by herd immunity. Okay? And this is the fundamental result from epidemic models and epidemic theory, that in order to protect a population, we do not need to vaccinate, or we do not need to protect every single individual in the population. Okay? All we need to do is to protect enough such that we eliminate transmission within the community. Okay? So, in order to understand this conceptually, it's useful to introduce the concept of an effective reproduction ratio. So, you're already very familiar with the basic reproductive ratio, the average number of people an infected person infects at the start of an epidemic. If we think about what that means in the very early stages of an outbreak, it can be useful to visualize this as an infection tree. So imagine we have a disease with an R0 of 2. We introduce 1 infective, they infect 2 people. In the early stages of the epidemic, those 2 people will also go on to infect 2 people. And then those people infect 2 people, and so on. Okay? In practice, we wouldn't see this completely uncontrolled growth and spread of the disease, because as the disease spreads, individuals are either removed or recovered which reduces the chances that infectious and susceptible individuals will meet each other in the population. So we expect that as a disease spreads, it burns through the fuel in the population that's driving that epidemic, and we see a reduction in the chance of spread. And this is what we capture with an effective reproduction number. Okay? So the instantaneous value of this, or we expect that the value of R0, which would be beta times the infectious period, will be reduced proportionately to the proportion of susceptibles that we have remaining in the population. Okay? So the less susceptibles there are in the population, the lower the value of the effective reproduction number R. So in a well-mixed population, we can define the effective reproduction ratio just by multiplying the value of R0 by the fraction susceptible in the population. Okay, so what does that mean if we think about our cartoon that we elaborated here with the infection tree? So let's imagine we have this disease with R0 equal 2 again, but instead of having a fully susceptible population, we have gone in and we've vaccinated at random half of the population. Okay? Then that first individual who's infected will, on average, be likely to meet one susceptible and one vaccinated individual. Okay? So if we go to the next generation, it's only that infected individual who can transmit. And so we can color this tree now by the individuals that are protected by the vaccine, and then these green individuals who have not been vaccinated but are protected because other individuals have been protected. So this is the impact of vaccination on transmission rates, or the so-called herd immunity effect. It's a property not of individuals, but of the herd of the population. Okay, so technically, how do we go about incorporating and modelling vaccination within this simple epidemic model framework that we have been working with in the practicals this morning? So here we have an SIR model, and this time I have expressed the transmission term in terms of the force of infection, okay, which I've defined down here. It's just frequency-dependent transmission. If we want to think about going in and doing a one-off vaccination in a population, effectively that's just changing the initial conditions of our model. Okay? So we just change how many individuals are in the recovered or the susceptible state. So a vaccine that is perfect, we can just assume has the same immunity as a recovered individual. Okay? So for our simple epidemic, if we look at the value of R effective, it falls as the disease spreads and then crosses the critical value of 1 at the peak of the outbreak. Provided R effective is less than 1, we have no epidemic and the population is protected by herd immunity. Okay? All right. So the critical, it can be shown that the critical vaccination threshold then is just given by the elimination threshold, 1 over R0, subtracted from 1. Okay, so this gives the theoretical proportion of the population that we need to vaccinate in order to ensure that the susceptible proportion is less than 1 over R0. I've been a bit clumsy there, but does that make sense? We happy? Good. Okay. So provided this is the case, then the disease will not cause an epidemic. Okay. We don't, in fact, I can't think of a situation where we would have the luxury of being able to go in before the disease is in the population and vaccinate the population ahead of time. Yeah. most often when we're thinking of control by vaccines, we're thinking about endemic infections which already have some circulating level of the disease. So our introduction of vaccination is either through vaccinating children before they become infected or through sort of targeted interventions. So let's just think about how, in practice, using vaccines, we have managed, in that one example, to eliminate an endemic disease. So there are, in fact, 2 infectious diseases we have managed to eradicate. Rinderpest is the other one, which is a disease of cattle. But smallpox is the only disease which we have managed to eradicate from the human population. And there's some very good reasons for this, in that it had characteristics which made it really an ideal candidate for an elimination program. Most important of which, it was only a human infectious disease. So there were no animal reservoirs to worry about. So that once we eliminated it from the human population, well, up until recently we were done. Although the increasing spread of Mpox, which has cross-reactivity with smallpox, is an illustration of how elimination poses potential further threats that other diseases can invade and occupy the same niche as the disease we've eliminated. But that's by the by for today's conversation. I've put high levels of morbidity and mortality as a sort of plus point for eradication here, and that might seem a little bit strange, but it costs a lot of money to eliminate an infectious disease. It costs a lot of time and effort. So if we're going to do that, there needs to be an important reason to do it. Lifelong immunity after recovery from infection and an effective vaccine, also key requirements for an elimination program. I haven't put it on here, but actually another key thing which pushed us down the road to elimination was, although the vaccine was effective, it wasn't very safe. So it's a very antigenic vaccine, and in many countries which had managed to eliminate smallpox, they wanted to stop using the vaccine because they were seeing more side effects from the vaccine than cases of the disease. And that's a big reason why the money was put in from the countries that had managed to control the disease and eliminated it to help in other countries to push the disease to elimination. Okay. When we think of elimination by vaccination, the first thought is just that we achieve it through routine vaccination. And that was an important part of the story for smallpox. So how would we model routine childhood vaccination? Well, it's a very similar picture. So we now have the SIR model with births coming in. But in the first instance, to first approximation, we can model the effect of vaccination as shortcutting the infectious state and susceptible and infectious states and just having births pushed into the recovered state. Okay? So this is a decent approximation provided your mean age of infection is much higher than the age at which you deliver the vaccine. Okay? Sorry?
Can you comment it?
Can you repeat it? Okay, so this is a reasonable approximation provided that the age that you vaccinate is much lower than the mean age at first infection. Okay? So if your mean age at first infection is comparable to the age that you can actually deliver the vaccine, then you need to think much more carefully about the age structure of the population. And we'll come back to that actually with the rubella example that's coming up. But if you have a disease where you have a much higher mean age at first infection, then this is a reasonable approximation to vaccination at birth. Okay. So vaccination can be thought of as effectively reducing the birth rate into the population. Mechanistically, it's the same. And in fact, we could go a bit further and say that there's an equivalence to reducing transmission rates as well, but that's a bit more subtle. while this works, we might want in our model to bookkeep the number that we vaccinated and actually have a separate compartment for vaccinated individuals. And that allows us to model more exotic vaccine effects, which we'll come to talk about tomorrow, which may affect other aspects of the life history of infection rather than just whether or not you get infected. So that sort of model would look a bit like this. And again, this is sort of how we deal with the problem in compartmental modeling. We add another compartment. Okay? And now in this case, the vaccinated individuals go in here and they have background mortality. And we're assuming in this case that they have perfect protection from infection. Okay, so we get this extra compartment means that we get an extra differential equation. The SI and R equations are pretty much unchanged, but we now have this birth term of vaccinated individuals and background mortality. Okay. We've got some evocative arrows there. I don't have anything to say about that. Okay.
What's the
So this is, that should be a mu. That's a typo. That's a typo. It should be mu. That's the mortality of the vaccinates. I could cover myself and say we might want that to be different because the vaccinates may have had a boost to their life expectancy, possibly. Okay, so we can analyze this model in exactly the same ways we did before, and that you've done a little bit yourself in the practical session this morning by finding the steady state and the equilibrium number of cases once we introduce vaccination. Okay, so if we first set the di by dt equation to 0, then we get the same expression for the susceptible fraction, okay, as the SIR model. Okay. Does that make sense? Does that surprise you? So no matter what our vaccine coverage, we have exactly the same susceptible fraction at equilibrium. Is that intuitive? It's a little worrying, isn't it? It's a little worrying because you're thinking we're doing all this effort, we're vaccinating all these kids, but we've got exactly the same amount of susceptibles in the population as if we hadn't bothered doing it.
The vaccine should make them less susceptible.
Why is it the same? Why is it the same? So two things are happening. Yeah, we're protecting individuals. Sorry?
And maybe those that were vaccinated are dying, and there are more births that are unvaccinated.
Yeah, so there's a balance, yeah?
I think because the vaccinated become recovered, so the time to reach equilibrium will reduce because of vaccination.
Okay, we're not thinking of the time at all here. This is sort of at steady state. The time will be affected. But what's happening here is that vaccination, we have conservation of people. Vaccination is just shortcutting to the recovered state. So the proportion susceptible is actually exactly the same, but as is the number of recovereds in the population. What's changing is the proportion that's infective at that equilibrium and the proportion that are infected. Okay? So it's this idea that we're shortcutting to immunity. Yeah? It's not that less infections happen because there's a lowered rate of transmission in the community, there's less available individuals to be infected, but those susceptibles are in some sense being protected and are still there because they haven't got the opportunity to be infected. Okay? Okay. So we can do a bit of algebra and get an expression for the fraction infected at equilibrium in terms of the parameters of the model, and it's nearly the same. as the SR. It's got this extra term related to the proportion of births that we're vaccinating. Okay? So if we look at the fraction susceptible, then yes, if we're looking over time, there's a slight difference here, as you said, with the population with vaccination and without. With vaccination, there's actually there's a slightly different trajectory towards the equilibrium. There's a slight change in the period of these oscillations because the transmission rate is a bit lower. But effectively, the threshold to prevent an epidemic is exactly the same as it was without vaccination. If we look at the infectious proportion as a function of vaccination coverage, then we see this effect that as the vaccine coverage increases, the number of infectious individuals at any time and the number of cases in the community over a time period is dropping linearly with the vaccine coverage until we hit the critical vaccination coverage, and then the disease is eliminated. Okay. So the critical vaccination threshold is exactly the same in a population with demography or a simple epidemic, simple population with no births and deaths. Okay. And that is why the concept of the basic reproduction ratio R0 is so important, and why estimating the value of R0 for a disease is so important, because that sets the amount of effort that we need in order to control the infection. And that could be effort in terms of any control measure. In the case of vaccination, it maps to the critical level of either births into the population or proportion of the population that we need to vaccinate in order to prevent epidemics. Okay? So if we look at smallpox, it's here, an R0 of just below 5, a routine level of coverage of just under 80%. If we compare that to other infectious diseases we might want to control, so SARS, the original SARS was an interesting case. It had a lower R0 and some interesting aspects to its transmission, which made it much more amenable to control by contact tracing and isolation than SARS-CoV-2 was. Chickenpox has a slightly higher R0, so we'd expect that to be more difficult to eliminate through vaccination. Measles has...
No, you can't see it on that screen because the colors are there.
Yeah, I was going to say measles has disappeared. Measles, which is the next on our target for elimination by vaccination, much, much bigger challenge than smallpox because of the higher, vastly higher reproduction ratio and the higher level of coverage required. Something like influenza H1N1 though, much, much lower R0. This is maybe even a bit high. Influenza R0 is typically thought to be just above 1 in most seasons. So why can't we eliminate influenza? Why have we not managed to do that?
Because of antigenic shift.
Yeah, because it's a horrible virus, which is, it's not one virus, in fact, it's just constantly changing. There's loss of immunity. The vaccines do not provide perfect protection or only provide protection against single antigenic variants.
Excuse me?
Yes?
Does the R0 vary according to country? Like the R0
Yes, absolutely. Absolutely. So if you go back and read Anderson and May's textbook, they have this lovely table of R0s for infectious diseases. And all those R0s are estimated in the same way, basically from data from England and Wales. You would absolutely not expect the same R0 in different countries because it's a function of the contact patterns, the risk of transmission, which might be mediated by climatic variables, susceptibility in the population, genetic factors. So It's going to be more similar than different in different contexts, but you absolutely wouldn't expect to be able to just take the same value and use it in a different population. So, are not incredibly important determinant of how easy it is to eliminate an infectious disease. It's not the only one, though. Okay. As I've already touched on, one of the most important reasons we managed to eliminate smallpox is that there was this incentive for countries who have had eliminated it to put the money in to eliminate the pathogen globally, which otherwise would not have allowed it to happen. The other important aspect is that smallpox was not eliminated by just routine use of vaccination. In the final stages of elimination, there was a lot of work done on contact tracing and ring vaccination to chase down those last final cases. And that's because once you get to a very low level of incidence, those heroic assumptions that we make in well-mixed models break down, and your contact pattern, your contact network between individuals becomes so much more important for the risk of transmission and enabling the persistence of an infectious disease, even at low levels, when a simple model would suggest that the disease should have gone extinct. Okay, so let's have a little change of pace, and let's think about the implications of these herd immunity effects of vaccination in terms of the distribution of disease in a population with age. So we've already talked a little bit about this link between the force of infection in a community and the age distribution of cases and susceptibility. Okay, so in a well-mixed population with a force of infection, which is frequency dependent, we can show that there will be a relationship between the mean age at first infection and the force of infection, such that the mean age of infection is inversely proportional to the force of infection. The implication of that is that the probability that you will be susceptible in a population will have an exponential distribution. Okay? And likewise, the distribution of cases in the population will be exponentially distributed. So for diseases like measles with a high force of infection, pretty much everyone is going to have been exposed and infected by the time they're 20 years old. Okay. So I motivated this relationship yesterday by asking you to think about the risk of experiencing the disease as affecting the age at which you become infected and become positive. If we think about what happens when we vaccinate, if we're reducing the transmission rate within the community, that's going to increase the time that it takes for us to be exposed to the infection if we haven't been vaccinated. Okay? So a side effect of vaccination is that as the number of cases at equilibrium decreases, the average age of first infection for those that haven't been vaccinated will increase as the vaccine coverage increases. Okay, so this is for a well-mixed population, just showing as you increase the vaccination coverage, the mean age of infection for this infection is going from below 5 years of age all the way up to 100. Okay, so ideally what you would hope is that by pushing the mean age of infection up beyond that of the life expectancy, you'll ultimately eliminate the infection. But at lower levels of vaccine coverage, changes in the mean age of infection could actually have unintended consequences for the distribution of pathology or morbidity due to a particular infection. And rubella is a really important example of why these effects can matter. Rubella itself is a very mild disease in children. It has very few side effects, very low rates of morbidity and mortality. However, when pregnant women are infected with rubella, it can lead to congenital rubella syndrome, which has absolutely horrific consequences for the unborn child. This is absolutely what you want to avoid and why you would want to control rubella. This is the main motivation, okay? Now, this poses a problem for the use of vaccination, because if we think about, so before vaccination, rubella has an R naught of around about 6, or at least it did in England and Wales. If we think about what that means for increasing vaccination coverage, then a vaccination coverage of about 60% would lead to pushing the mean age of first infection up from 10 to about 25, okay? So as a consequence, in a well-mixed population, you could increase the incidence of congenital rubella syndrome, even although you've reduced the amount of rubella circulating in the community. So this is what Anderson and May described as a perverse consequence of vaccination. Unintended consequence with highly negative impacts.
Sorry,
Yeah.
I didn't understand the why. Can you repeat that? So why you would increase the incidence?
So you increase the incidence because although there's fewer cases, they're concentrated in the child-bearing age group. Okay, so before vaccination, basically kids are getting it, and all of the kids are going to have been exposed to it, become immune before they reach an age that they might become pregnant. Yeah? When you vaccinate, you reduce the number of cases overall, but the cases that you do get occur in the older age groups, so you're potentially more likely to have infections in pregnant women than before you started vaccinating.
So does that mean it's like you are just postponing the disease ahead of time?
That's exactly what vaccination does. Yeah, it delays the exposure. If you're not vaccinated, it delays the time that you will be exposed. Yeah, this is one of the things we also saw this during the pandemic, because a lot of us in epidemiology were relieved that a vaccine came so quickly, and I think a lot of people who weren't in epidemiology thought, well, that solved the problem, where actually what the vaccine does is it buys you time. Yeah, it's not that the disease is postponing and stretching out how many cases you're going to have, which is, it's so important for saving lives because people die when the health systems are overwhelmed. But it's a difficult pill to swallow if you're thinking that the vaccine is solving the problem and protecting everyone.
I think we've seen the same with malaria, because that RTSS vaccine was designed to take when children are most vulnerable, which is when they've lost their maternal immunity, which ends at around 6 months. That's why the first dose is at 5 months.
Mm-hmm.
So 5, 6, 7, and then 22 months later as a booster.
Yeah.
But what we're seeing now is the age of infection of kids is in the school-age children. Yeah, so above 2.
Yeah.
So now they're saying, can you evaluate the vaccine in the school-age children?
Yes, so that's exactly what you would expect. That's exactly the sort of shift that you expect from a vaccine. Yeah. So conceptually, for a disease like rubella, or any disease where maybe the disease causes more problems in older people when they get infected, you need to carefully think about when you introduce a vaccine what the effects are going to be, not just in the next 5 years, but in the next 10, 20, 30, 40 years. A well-mixed model will give you a prediction, but it is almost certainly the wrong prediction, because the detailed change in the mean age of infection will depend on the contact patterns and the contact structure within the population. Now, when Anderson and May were first sort of talking about these problems back in the 1980s, we basically made guesses about what the contact structures in populations might be. We are lucky now that we have lots of cases of social mixing data, which gives us more information on what we think the structure of age structures are likely to be. Although, as we saw during COVID, and as Katie talked about, this can change in response. This does change over time and can change in response to disease spread. But getting that right and thinking about the relationship will depend quite sensitively on the details of those assumptions about age structure. So when thinking about long-term impacts of vaccination, you need to be very careful with your sensitivity analyses and consider lots of different scenarios for age mixing, how it may change over time, to assess what the relative risks might be and benefits for a vaccine. Okay.
So please, how about for vaccines that covers you for a lifetime?
So this effect is absolutely for vaccines that are perfect and that cover you for your lifetime. So actually leaky vaccines, where you have loss of immunity, are going to have less impact on the mean age at first infection. Or they're going to have a different impact at the mean age of the first infection. So this effect comes from having a very effective vaccination with perfect immunity, because it's not, these things are not happening to the individuals that are vaccinated, it's the ones that don't. Yeah? So in fact, the original Anderson and May work was motivated by the introduction of the MMR vaccine in the UK, because before that we just vaccinated schoolgirls with a rubella vaccine at 16 in order just to mop up any susceptibles that might still be there to prevent CRS. And when MMR came in, there was this concern that if we don't do it properly, if we only vaccinate 60%, we're maybe storing up a problem for us in about 2010, I think their model said. What happened in practice is we hit 90%, at least before the Andrew Wakefield scandal. We got a very high coverage, which meant we didn't have any problem, or we haven't had a problem yet. But with recent falls in vaccine coverage, it's just one of the concerns that we might be storing up a problem for rubella as well as the other infections in the future. Okay. All right. So reduction in transmission from a vaccine makes it the most effective method of control. It also has these unintended consequences in terms of the change in the age distribution of cases. The age distribution or the age structure within a population also offers opportunities to better target the use of vaccination to be more effective. And to motivate that, I want to now consider a relatively simple two age group model where we would consider adults and children as two separate age groups, okay, where there's transmission within the children, within the adults, and between the adult and children groups. Okay, so this is the same example that Katie used yesterday. So rather than having a single reproduction number, we now have different individual reproduction numbers for the individual groups within the groups. So R11 here would be the reproduction number within children, R22 the reproduction number within adults, and R12 and 21 represent the cross-group transmission. Okay? So the next generation matrix can be thought of as a generalization of R0. Okay? So in the tree that I generated at the beginning of this lecture, I showed how we can use R0 to basically count the number of cases that we have in each step. Okay? The next generation matrix plays the same role, but the difference is the number of new cases we get will be weighted by the proportion of the population in our different age groups. Okay? Does that make sense? This is a bit subtle. So we have this matrix here, but then we have this vector which tells us how many kids and how many adults we have. And the more or less of each group will change the effective reproduction ratio in our population. Okay? So the effective reproduction ratio in a structured population will be a product of this next generation matrix and the distribution of susceptibles in the population. Okay? And we'd work that out using matrix algebra, which we don't really have time to get into, but I'm happy to talk about with anyone who wants to know about it. And Katie also alluded to the fact that the overall R0 for the population will be calculable by this thing called the maximum eigenvalue of the next generation matrix. Now, I would love at this point to tell you about eigenvalues and eigenvectors. They're a very simple concept as long as you've done 2 terms of linear algebra, because they depend on a whole bunch of other concepts. At some level, it's enough to know that they are just a thing that we can calculate from a matrix. And actually, we'll go through the calculations. The calculations are easy. Understanding what they are is a bit more tricky. To get an idea of them, there is a fantastic video here that I have linked on YouTube, which visualizes what eigenvalues and eigenvectors are in terms of matrices and vector transformations. And Katie needs to stop me from blethering for too long on exactly this point. But if you watch that video, it will suggest you watch 6 other videos before to understand that video. And that's why I can't talk about it too much. But essentially, the eigenvector of a matrix is the direction in which you'll see the maximum change when you multiply this matrix by a vector. And what that means practically in epidemiology is it's the combination of susceptibles in the different age groups that will lead to the greatest number of new cases. Okay? Finding the eigenvalues, and the eigenvalues give you the magnitude of that change, and the eigenvectors tell you essentially what the combinations of kids and adults are that will give you that maximum change. Okay? That's all I'm going to say about that. Yeah.
Just a quick question. So it means, okay, so the other method for finding R0
Mm-hmm.
and this, the next generation method is useful when you have like different groups of population. Is that what that means?
So they're more or less equivalent. So in fact, you can use the next generation method to calculate the R0 for a disease with one compartment. It would just be completely overkill. Yeah? Complete overkill. But it gives the same answer. And that's critical. It does give the same answer. There are different ways of calculating R0 which give different answers, but not in this case. If you have more than one infectious state in your model, which is either because you have asymptomatic and symptomatic, or you have age structure or spatial structure, you need to use this to do the averaging correctly. And it is a procedure which Katie is going to take you through in more detail, which you can apply to any model to calculate what the R0 of that model is. Okay. The mechanics of it come to calculating this property of a matrix called the determinant. And the eigenvalues are the solution to this matrix equation, where the next generation matrix, where it has elements A, B, C, D. The eigenvalues are these purple numbers lambda. Okay? And when we plug in the equation for a determinant, what we get out is something that should be very familiar to you. It's a quadratic equation. Okay? And it's a quadratic equation in this case because we have a 2 by 2 matrix. We have 2 different infectious states. Okay? If we had 3 infectious states, we would get a cubic equation, and so on. Yeah? So the more states we have, the more potential, the higher the power of this polynomial expression that we get to calculate the eigenvalues, and the more eigenvalues there will be. Okay? So we'd expect there to be 2 eigenvalues at most in this case. We can see that by plugging in the formula for the solution of the quadratic equation. Now this looks horrible and looks a bit different, I'm sure, but that's just because we've substituted in these numbers from this equation into the solution for the quadratic equation. So you'll see the familiar square root and the plus or minus. Yeah? So depending on the value of the discriminant, we'll either have 0 eigenvalues, 1 eigenvalue, or 2 eigenvalues. Okay? Yes? Yes. Yes, and in fact, the next generation matrix could define a Markov chain. You could use it to define a Markov chain. Yes. Yes, so there are similarities there. In that, yes, so in a Markov chain model, the generator matrix takes you from one state of the model to the next. Yeah? And the next generation matrix plays exactly the same role, but it would only be valid until you get susceptible depletion. But absolutely, and you can formulate a stochastic epidemic model. We won't be doing it tomorrow, but you can do it using exactly that framework. Okay, so I've done that horrible thing and said it can be shown and skipped over a lot of algebra, but the reason for that is we can get this rather neat result for an epidemic model with 2 age groups, where the value of R0 is given by this closed form solution. Okay? So if we plug in the numbers from the next generation matrix we used yesterday, we can get the same value that we got before, an R0 of 2.14. Okay? But the cool thing about this is we can now think about how might we best target control measures. Okay? So we know that this average R0 is going to give us a critical vaccination threshold, yeah, at which if we vaccinate at random in the population, we'll be able to prevent transmission. Okay? But it turns out we can actually do a bit better than that. So here we have the critical vaccination threshold for the average value of R0 of 0.53. But what if, rather than vaccinating at random, we weight the proportion of children and adults that we vaccinate? Okay? So we write the total number vaccinated as the number of children vaccinated plus the number of adults vaccinated. Okay? So our next generation matrix now, yeah, is taking into account, so we're going to calculate the effective R here. It's taking into account the proportion that are susceptible in the children, 1 minus VC, or in the adults, 1 minus VA. So in the same way as we formulated that effective reproduction ratio for the well-mixed population, we reduce the components of the next generation matrix by the fractions in the 2 groups. Okay? And then we can show, well, my friend and colleague Ellen Brooks-Pollock did this, she did the maths, and got this nice expression for R effective, which you can then, if we identify the fact that control corresponds to an R effective of 1, we can rearrange that expression to get this slightly horrible looking expression yeah, which tells us for any particular value of VA for the adults being vaccinated that we choose, it tells us how many children we would have to vaccinate, or vice versa. For a particular number of children that we target to vaccinate, we can calculate the number of adults we would need to vaccinate to achieve elimination. Okay? And we can sanity check this. It's always, I think it's always important when somebody like me pulls an equation out of their hat, you should look at it and think, does that make any sense? Okay? And if we set VC to 0, okay, this term is going to disappear, or this is going to become 1 minus 2, so that's 1. This term is going to be this worked in my head when I did it earlier. Oh. Okay, we'd need to do a bit more work, actually. But if we did that and rearranged it, we would get 1 minus 1 over the R for the adults only if we set VC to 0. And likewise, if we set VA to 0, what we should end up with, exercise for the student, is the expression 1 minus 1 over R naught for the child compartment. Okay. It's a horrible expression, but it makes a nice, simple, easy to interpret graph. Along here, we have the percentage of children vaccinated and total percentage vaccinated on this axis. Okay? So this is the line where R effective equals 1, so the elimination threshold. So if we plot the well-mixed, using the well-mixed equation for 1 minus 1 over R naught, then it is here, where we would be vaccinating about 55% of children and just under 60% of adults. Okay, so that's under random vaccination. Okay, but what the graph shows us is that it would be more optimal to vaccinate, to preferentially vaccinate the children, yeah, then we would need to vaccinate less adults and less total vaccines overall in order to eliminate the disease in this population. Okay? So by targeting the children, we need to use less vaccines to achieve the same result. Okay? So that's come through from the mathematics. Intuitively, does that make sense to you? To understand, why would we target the children? Yeah.
Because they have more contacts.
Yeah, they've got a higher rate of transmission. They're contributing more to transmission. They're what we call a core group. Yeah, they are horrible, disgusting little blobs that are interacting with each other and then giving the diseases to me, their parent. So there's a general, so this is a sort of specific result for this population, but there's a general result, which is important, that if we target core groups for transmission, we will always get a bigger benefit to vaccination. And this is something that is used practically in vaccination programs around the world. In particular, Japan found that by using influenza vaccine in primary school kids, they could actually have a bigger impact reducing morbidity and mortality in the elderly than just protecting the elderly with vaccination. And that's been repeated by the UK and I think maybe the US and other countries since then. So we now routinely do this in the UK, which is of benefit both to the children and their parents, i.e. me, as well as having a bigger impact on mortality in the elderly. Okay, the key and most important message of this lecture, though, is that the reason we are here in a model about in a course about infectious disease modeling is that herd immunity, the concept of herd immunity, changes the way we think about disease control away, it reframes it away from protecting individuals to reducing transmission within the community. That's always going to be the more effective and more important way to eliminate a disease. And when we have heterogeneous populations, targeting core groups can be a way to more effectively use limited vaccine resources to achieve the same ends. Okay. Any questions? Stunned. Oh, no.
So, in a simple SIR model,
Mm-hmm.
how do you compute the indirect effects, the hard effects?
So what do you mean? Because I could answer that a few different ways.
No,
So
So what I'm trying to say, I come across a lot of papers that are trying to estimate the direct and the indirect effects or impact of vaccination, but they are never clear how the add effects are computed in a compartmental.
So in a real population, what we measure is the cases averted, which is going to be a measure of both the direct and the indirect protection. In a compartmental model, we could bookkeep the number of infections that we have, and we could calculate the reduction in cases that comes just from the reduction in transmission. Offhand, I can't remember how to do that, but we could calculate that from within a model. In a stochastic in a real population, in order to tease that apart, what we would have to do is to look at the cases averted in populations which have different levels of immunity or different levels of vaccination. So in any realistic scenario, it's almost impossible to tease out what the direct and indirect protection you're getting from a vaccine is. What we see is some messy average. There's ways we can estimate it using experiments, and there's ways we can do it by cleverly looking at different populations. And I'll come back to that and talk about that in, I think, tomorrow's lecture. It's a tricky thing. You have to really know how your vaccine works as well, because some vaccines may only have an effect on transmission but have no direct protection from infection. Yeah. So your question's really important and difficult, and it's got a different answer, I think, in model world than the real world as well. Okay. So we'll maybe come back to that one later. Okay. All right, do we want to have 5 minutes before we launch into probabilities? Yeah? Okay, so I will start sharp at 25 minutes past 12. Yes?
One of the slides you put, why haven't we eradicated measles?
Mhm.
Maybe you could throw more light to us the group about elimination versus eradication.
this is the last piece of maths refresher that we need, and it's mainly in here to just remind you or introduce some terminology, some rules that we need for dealing with mathematical probabilities, which we'll be using when I talk about and introduce you to stochastic models tomorrow. So probability theory it's a very unusual part of mathematics in that it is motivated entirely by a real-world application in terms of understanding how likely it is things are to happen. It's the basis of pretty much how we interpret all experimental science and statistics. It's the language of statistics, but it's also one of the most abstract and rules-based areas of mathematics. So it can be a bit dry. I'm going to try and keep this snappy. I think it's hopefully some of these concepts you'll have seen before in your life. I think it helps to get them a number of times from different perspectives. It's certainly an area of maths I only really understood after about the third or fourth course I had successfully passed before it really sort of sunk in. So I hope my perspective on it will be useful to you today. So we're going to talk a little bit about the concept of probability, its mathematical definition, and the rules that we have, the algebra for dealing with probabilities, which are a very special type of number and of special properties. We're then going to introduce random variables. So these are the outcomes of random processes or experiments, which can be described by probabilities. And that leads finally to the ideas of probability distributions, which are fundamental importance both for statistics and for the stochastic modeling we get onto tomorrow. Okay, love to start with a definition. So probability can be defined in a formal way as the number of favorable outcomes divided by the number of possible outcomes, okay, for any sort of process which is either random or subject to chance in some way, okay? So just to firm that up, if we think about taking a fair and unbiased coin and tossing that coin, we would expect that the probability that that coin comes up heads after a fair coin toss will be approximately a half. Okay? Seems intuitively right, but formally we can define and calculate that as the number of favorable outcomes, so getting ahead, divided by the number of total outcomes, either a head or a tail, to give a half. Okay. So what if I flip a coin twice? What's the probability of getting two heads? Anyone? Be what? A half times 2? So that would be 1. So we're guaranteed to get it. That doesn't sound right. That doesn't sound right. 1/4? I like the way you're thinking. That's not right, but I like it. That would be a half. So if we count it out, what are the number of outcomes that we can get? We can either get a head and a tail. We can get Katie. Should have done. She was really clever and she put in the Kenyan shilling here. But we should have head and a tail, and we should have tail and a head because the order matters. Yeah. And what's happened to head and head?
Tail and tail.
Wait, am I doing this the wrong? What? They're all the same. That's not any good. Oh, okay, I'm defeated. Okay. If we tabulated it out, we would find that there's one favorable way to get 2 heads out of 3 possible outcomes, because we can get a head and a head, or we can get tail and a head and a tail. Okay. Which would have been nice to have there, but we'll fix that. So
Wait, it's the same coin, right?
No, it's 2 points.
Oh, it's 2
So it's 1
points.
over 4. It's 1 over 4.
Yeah, so you can.
You get a head and a tail. 2 heads and 2 tails. So it's 1 over 4. It's 2 points. It's 1 over 4.
yep.
It's 1 over 4.
I think this guy's going to sort us out. Yep.
Okay. I think the outcomes are 4, because you'll have a head and a head. The 4 possible outcomes. Yeah, it's 4. Let me explain, eh? No, it's a 1 coin twice.
But there's 2 trials.
Yeah. Okay, let me explain and then you explain, eh? Okay, it's 1 coin which is flipped twice, yeah? So you can get a head on the first flip and a head on the second flip, eh?
Yep,
Yes.
that's one.
Then a head and a tail, then a tail and a tail, then tail and a head. So there are 4 possible outcomes. Yes.
And
Yes.
there's 1 favorable.
Yeah, only
Gives
1.
us a quarter.
So it's
Why is
a 1
Matt
over 4.
got a third here.
Yes. Exactly. It's just the same like flipping
Yeah.
2 coins once. 2 coins once, yeah. It's the same as flipping 2 coins once.
Right. It should be 1 over 4. Yeah?
I'm glad that it should be 1 over 4. It means I'm not the only one lost.
Yeah, no. This is an example of how probabilities can be confusing and non-intuitive. Sorry, we're going to blame Matt Castle for the 3 and Katie for the picture. And me for originally writing these lectures 12 years ago. Okay, so it should be a quarter. And we can work that out just by enumerating all of the possible outcomes and being very careful in countering them. So all of that is assuming, of course, that I am a fair and honest man, which, given my attempt to convince you the answer was 1/3, you probably shouldn't trust. So, if that coin was biased in some way, then our calculation of the probability would be wrong. We could test that hypothesis. We could test the outcome by taking the frequentist interpretation of probability and just doing a lot of experiments and seeing what we estimate the probability to be. So if I flip a coin repeatedly, what is the proportion of times that it comes up heads? Okay, so here we have simulated this, and I'm using this in the statistical sense of the word, in that we're running a random process, okay, where the probability was 1/2 each time, okay, and we see that after a very long number of trials, 1,000 trials, the estimated probability converges towards 1/2. Okay? With initially, there's a lot of variation. Okay? But in principle, this is the frequentist definition of probability. We can define or we can estimate the probability that something happens by just doing it lots of times, recording it, and averaging. Okay. But often we don't have we aren't able to perform a large number of trials, or we might not be able to perform a trial at all. So there is also a subjective interpretation of probabilities, in that we could interpret or we could assign a value of a probability as representing a degree of belief that that particular outcome will occur. Yeah? The value of 0 implying that the outcome's impossible, and a value of 1 that it's certain to happen. Okay? Okay. All of these definitions in some sense should be consistent with each other and should only cause arguments if you get a frequentist statistician in the room with a Bayesian statistician. So I'll leave that to TJ on Saturday. All right. We've already talked about Venn diagrams and used them before. They're a useful way of making sure you don't get yourself in a pickle by counting the number of possible events in the wrong way. The entire sample space, or the entire range of events that can happen, is described by a box. A particular event corresponds to a subset of that box. So we could bisect our Venn diagram to have heads and tails taking up 50% of the box. If we're really fancy, we might put in a small probability that it lands on the edge. Okay. The choice of the sample space is not unique, and events can overlap. So we may have mutually exclusive events, such as individuals who are healthy and infected, but we may likewise have categories which are subsets of other categories. Like if we have infectious individuals, we may have a symptomatic group and an asymptomatic group. Okay, we're going to use these Venn diagrams just to go through some of the rules and basic results which allow us to combine together probabilities to calculate the probability of multiple events happening or different events happening in different orders, because it's rather clumsy to always start listing out the possible number of events and drawing out a Venn diagram and work it out. So it's useful to derive these rules so that we have a way of calculating and working with probabilities that respect the properties that those numbers have. Okay? So, bit of notation. A is going to be the name of the event we're interested in, and then the probability that A occurs will be P of A. So, taking the frequentist definition of probability, we can consider that the probability of A is going to be the size of A, so the number of events that correspond to that outcome, relative to the size of the sample space. Okay? So if we're thinking of rolling a single die and our event is getting a 6, then the probability of getting a 6 will be the size of that, which is 1 way, divided by the size of the space, or a 1/6. Okay? All right. Since the probability is constrained between 0 and 1, it means that if we know the probability of something happening, we also know the probability that it doesn't happen. It's just 1 minus that probability. Okay? Easy, very useful though. We'll be using that later. If we have multiple events, then we can calculate the probability that both events happen. Okay? And that's given by the intersection of the sets of numbers in A and B. Okay? So by finding the intersection of the two sets, we can calculate what the probability of A and B both happening. And Matt's got a third here again. What is going on with these slides? So that's 2 out of 6. No, this one's right. This was right. It's 2 out of 6 reduced to a third. Okay. Because A is even. Okay, so A is even, B is greater than 3, A and B is 4 out of 6, 2 out of 6, which is, okay. It's fine, it's just a weird example. Sorry? Yeah. Yeah, yeah. No, that's true. Yeah. Okay. This is fine. Okay. We might also be interested in the union or the probability that events A or B occurs. Okay? So again, if we look at the Venn diagram, that's the joint area of A and B together. But if we only know the probability of being in A and B, we need to be careful to count for the intersection between the two groups. Okay? So if those two events are what we call mutually exclusive, so the probability of A and B is 0, then we can just add. Okay? But if the probability of A and B, if there's any intersection, if there's any elements which can belong to both A and B, then we need to correct for the probability of A and B. Otherwise, we'd be double counting the number of outcomes in the union. Okay? Does that make sense? Okay. So when we want to add probabilities, we need to be careful that we know what the probability of A and B is, or that it's 0. Okay. Finally, we need to be comfortable with this idea of conditional probability. So sometimes an event will affect the probability that something else happens. So we consider rolling a dice. What is the probability we get a 6? How does this change if we already know that you rolled an even number? Okay? So if we get that extra bit of information, the probability that we've got a 6 changes. Okay? And in this situation, we say that the events are conditioned on each other. Okay? So we say that the probability of A given B is the probability that A occurs given that B has already occurred. Okay? So if we just use the same rationale that we did before, probability of A given B is the size of A and B relative, not to the size of the sample space, but to the size of B. Okay? So the probability of A given B is the probability of A and B divided by the probability of B. Okay? So that's just how we would calculate a conditional probability. What turns out to be even more useful than this, though, is if we rearrange this to write that the probability of A and B is equal to the probability of A given B times the probability of B. Okay? And this turns out to be incredibly useful for many things, including Bayesian inference. Okay? So we'll be using this a lot later in the course. Of course, sometimes if the events don't affect each other, then probability of A given B will just be the probability of A, or vice versa, and we say that the events are independent, and that makes it really easy to calculate the probability of both events occurring. For independent events, we just multiply the probabilities together. So if events are independent, it makes our lives a lot easier as probabilists and as statisticians. And in fact, often as statisticians, we like to assume that the events are independent because it makes our lives so much easier. Okay. That is a whistle-top tour of probabilities, really just for reference. The most important concept we want to take forward, though, is this idea of a random variable and a probability distribution. So a random variable is what we call a quantity whose value depends on the outcome of a random process, which could just be an experiment. So a measurement is a random variable. Okay? Rolling 2 dice is a random process which we could define lots of different random variables. Okay? And a random variable can take potentially any value. So the highest number from the dice could take 1, 2, 3, 4, 5, 6. The number of sixes, the sum of the 2 dice. Okay? We can describe how likely it is we are to see different values of a random variable using probabilities. Okay? So we can calculate what the probability is that a random variable x has any particular value. Okay? Does that make sense? Okay. All right. So just to make a solid example, let's say x is the highest number obtained when throwing 2 dice. And so x can take values from 1 to 6, and we can tabulate them all out. And we can explicitly calculate in the table what is the probability x equals 1, 2, 3, 4, 5, 6. Okay? So we get this set, this table of probabilities, which effectively tell us everything about this experiment. All of the outcomes that can happen and how likely each of the outcomes is to happen. Okay? So if we plot it out, what we have created here is the probability distribution which describes the random process x, the random variable x. Okay? The most likely outcome is that we get a 6. The least likely outcome is 1. Okay? All right. What is the average value of x? If we wanted to calculate the average value of x, how would we do that? Sorry? Oh, if we wanted to calculate the average value of x, so we know, from this distribution, we know how likely it is to get each of the different values. What would the average value be if we did many, many experiments and averaged? We could simulate to do that, but from the distribution, how could we calculate that from these probabilities? Sorry?
We are supposed to find the probability of each of them occurring over the sum of 4.
Yeah.
Add the probability of each.
So add these up.
1 plus 3 plus 5 plus 7 plus 9 plus 11 over 136. That should be the average.
Yeah. So if we, I think you've got it. So if we multiply the value by the probability, yeah, the probabilities give the weights, so the chance of seeing that value. So if we multiply the probability by the value itself and add it up, we get the average. Okay? So the probability distribution doesn't just tell us about how likely each event happens, but we can use it to calculate the average, the expectation. We can use it to calculate the variance, the variability, the standard deviation, and all the higher order moments of the distributions. Yeah?
Just thinking, if I'm crossing the die repeatedly, what makes it easier for a 6 to have a higher probability of,
I think
compared to 1?
It's one of these funny artificial definitions. Is choosing the highest number when throwing 2 dice.
Yes.
Yeah? So by the definition, you're always going to choose, out of the 2 trials that you've done, you're always going to choose the highest one. So it's going to be skewed towards the higher numbers. Yeah? Does that make sense? Okay. All right. So in this case, we can tabulate all the outcomes and calculate it. Again, we could just run lots and lots of experiments, and we could make an empirical probability distribution, which describes the data. So here, we simulated it 50 times, and we get something that looks quite like, but not exactly like the distribution, and that's because we really would need to run it for a lot longer to explore the tails of the distribution to get the exact value. But we'll come back to that idea in the probability practical later. Okay, so what we talked about here, the random variable x is what we call a discrete random variable because it can only take integer values. And for a discrete random variable, we have this probability distribution function, which we can calculate or estimate. It's sometimes referred to as a probability mass function for a reason that will only become clear in the next slide. But for now, that's just what they're called. And it could be any function provided it has these two properties, that all of the elements are positive and that it is normalized, that when you add up all the values of the probability mass function for the over the range of the variable x, then you get 1. Okay. Equally well, we can define random variables that are continuous. So the height of a person, length of an infectious period, time between emails. But we have to treat these slightly differently. And the problem is, if we think about what is the probability, let's say we have a measurement which goes between 0 and 2, what's the probability that the measurement is exactly 0.5? Okay, the favorable outcomes are 1. Okay, that's easy enough. But how many possible values do we have in the interval between 0 and 2? Sorry? 4? No, more than 4. So how many times can I cut up a line with continuous numbers? 20? There's no limit. It's infinite. Okay? Yeah? That's the whole point of a continuous number. You can always make it smaller. Okay? So for a continuous variable, the probability of actually picking one point is 0. Okay? It's not a sensible question to ask. Yeah? Because there's an infinite number of possible values on any interval. Okay? We can, however, ask the question, what's the probability that x is less than or equal to 0.5? Okay? Because then we know that there are, it's 0.25 because it's a half divided by 2. Okay? Yeah? Does that make sense? So talking about a range is a question we can ask and we can calculate and assign a probability to it, but we can't do it with a point. Okay? So that's why, in order to describe continuous random variables, we use something called a probability density function. Okay? So in this case, the probability density function looks like this. It's just a uniform distribution, okay? And in order to, the probability density function is defined such that the area under the density function corresponds to a probability, okay? So we say that the probability that x is less than or equal to minus 0.5 is the integral from 0 to 0.5 of the density function, okay? And this is where that mass language comes from. If we integrate a density, what do we get? We get a mass. Okay? Another way of thinking about this is we're summing up probabilities, so, but it's continuous, the summation turns into an integral sign. Okay? Standard trick that we use in mathematics. All right? So again, a probability density function can be any function. We can derive it from first principles, thinking about some physical process, or it can be something we measure, or just something we dream up, provided it has these two properties, that it's positive, that all of its values are greater than 0 over the range of the value of the variable x, and that when we integrate over the range or over the entire real scale, it is normalized. It has a unit area. Okay? And then if we want to calculate the probability that a random variable is in any interval between a and b, we just need to calculate an integral of that probability density function, either on pen and paper, or we ask the computer very nicely to do it for us. Okay, I'm going to stop there because that's basically what we need to talk. There's a few other we need to know, and we should all go and have some lunch. There's a few other examples here of specific distributions, but really this is just a bestiary of things that we might use and we might want to use, and things that you've probably seen before. Like the binomial distribution, something we use a lot in epidemiological modeling, particularly if we want to simulate the effect of underreporting of case data. So if we are only seeing a proportion of cases, then we would expect at any time interval the distribution of cases that we see will be described by a binomial distribution, okay, which counts the number of successes and failures that we have in a number of trials. Okay? We've seen normal distributions. I'm sure we've seen before. Gamma distributions have come up for infectious and latent period distributions. All of these probability distributions can be useful and can be used to calculate in the same way as we talked about for the discrete distribution, the mean and the variance. Rather than doing a sum, in that case, we integrate the probability distribution by the value of the random variable. Okay? Okay. We've done a very whistle-cap recap of the language of probability and the rules that we use for manipulating them. We've introduced random variables, continuous and discrete, probability mass and density functions, and distributions. We're going to now be using these concepts both in the stats part of the course and in stochastic modeling. But this is mostly here for reference to look back at and to ask me about. One final thing before we stop. Someone asked me in the break. I was using lots of words without defining them, which is very bad, and I should do that now. So I talked about, when I was talking about elimination and eradication of pathogens, they are terms which are often confused, mostly by countries who claim that they are eradicating disease, which is impossible. A country can't eradicate a pathogen because eradication is the elimination of a pathogen from the whole globe, from every country. Elimination is a reasonable goal for a country, which is bringing down the incidence or prevalence of the disease either below 0 or some acceptable threshold. Below that, you have trying to achieve control or officially free status, which is very much more common in animal diseases than human diseases, where you've given up on the idea you might eradicate it, but you just want to claim that you have the problem under control. Elimination, eradication, what else did I need to define? Was there something else?
In relation to measles, you asked a question. Why measles is not?
So the main reason is the complications with measles is the extremely high rate of transmission means that you need to achieve a very high level of coverage, which is difficult to achieve because although the vaccine is excellent, it's very difficult to deliver it fast enough in order to protect populations. So the high transmission rate means there's a very low mean age at first infection with measles, even in countries with vaccination. So you then hit what's called the window problem, where you need to wait for the maternal antibodies, which protect babies from their mothers, to wane. before the vaccine will be effective. So you get this very critical window where you need to get in, vaccinate the children before they get exposed to the disease. So the high rate of transmission is a big barrier. The costs associated with that and just the practicalities of getting enough vaccine to the right places to get to that end game of elimination. And I think another big factor, which is going to really compromise any progress towards eradication in the near future, is the countries which have eliminated measles basically letting the side down and slipping back, because we have got increasing problems with vaccine hesitancy because nobody sees measles in the UK anymore. Or you very rarely see measles. You're very unlikely to know of someone who has been severely affected or died. And that means parents don't want to take the risk of getting their child vaccinated because the balance has changed, the perception has changed. So I think, the wealthier countries who have had success in the past may end up compromising our ability to eradicate measles, sadly. Okay, all right. Thank you very much. Let's go and enjoy the lovely cakes and try and be back here to start at 2. And we are going into more eigenvalues with Katie. A little bit. Thank you.